Welcome back to AI Tech Pathways. Today, we're diving into a really cool reflection on Lecture 16 of the Deep Reinforcement Learning course at Stanford. We hear so much about reinforcement learning in the news, right? Machines mastering wild video games or complex digital tasks through just millions of automated trial and error attempts. But, well, here's the dirty little secret of modern robotics. When you take a system out of a perfect, pristine computer simulation and drop it into a physical robot operating in the messy real world, that whole automated trial and error process, it hits a massive brick wall. The physics don't behave, the hard work breaks, and things just get incredibly complicated. So in this explainer, we're going to unpack the exact tech pathways researchers are engineering to break through this barrier and achieve genuine physical independence. First things first, we kind of need to shatter the illusion of robot autonomy right from the jump. When you scroll through social media and see those incredible viral videos, a robot doing a flawless backflip, or running through a forest, or perfectly cooking a meal, what you are absolutely not seeing is the grueling, heavily supervised learning process that actually got it to that point. The practicing phase, it really isn't autonomous at all. Behind the camera, completely out of frame, the system is relying heavily on a totally exhausted human element. And there's this stark contrast between digital training and physical training. In a simulation, if a virtual robot tries to hand you a virtual cup of coffee and drops it, the programmer just hits a command, env.reset. Boom. The digital environment instantly restarts, the physics engine resets, and the cup is magically right back in the robot's hand for attempt number 2. Literally takes milliseconds. But in the physical world, you can't just type a line of code to instantly unspill hot coffee or glue a shattered ceramic mug back together. The physical world absolutely requires physical human intervention.
So here's our roadmap for today's explainer. We'll start with the illusion of autonomy, then look at the reset bottleneck. After that, we'll explore 3 specific tech pathways: forward-backward learning, multitask cycles, and finally, single-life adaptation. Let's see how these map out a complete solution.
Starting with Section 1, the illusion of autonomy, when every step matters. Before we fix the whole dropped mugs and spilled coffee problem, we have to look at how we actually evaluate an AI's learning process. Take a look at these 2 extremes, a Mars rover versus a robot chef. If you send a multi-billion-dollar rover to Mars, its continuing policy is what matters. Every single rocket scans, every tiny movement, even if it accidentally drives down a dead-end crater, that's all valuable scientific data. It's learning and succeeding simultaneously its entire life. But if you're training a robot chef for a busy restaurant, the criteria shift completely. You literally only care about the deployed policy. Can it cook and serve a perfect meal for a paying customer after all the training is over? That chef robot needs a completely safe, isolated space to fail, dropping dozens of eggs, burning steaks, way before it ever sees a real kitchen.
And because it desperately needs that safe space to fail, imagine being the human engineer stuck in the lab with this thing. Right now, you are the manual reset button. The Stanford lecture highlighted just how incredibly tedious this is. Picture a tired researcher fetching a physical hockey puck 10,000 times because the robot missed the goal during practice. Or someone manually pushing a door shut over and over just so the robotic arm can learn the precise torque to open it. Or an intern constantly smoothing out a crumpled towel so the robot can practice folding. Sure, the neural network is learning, but the human is basically doing half the physical labor.
Which brings us to Section 2, the reset bottleneck, why time isn't the answer.
So you might be thinking, hey, why not just let the robot run for much longer episodes so the human doesn't have to jump in as often? Like, instead of resetting every 1,000 steps, let it roam for 100,000 steps. Sounds logical, right? But mathematically, doing that completely breaks the machine learning process. It leads to 2 massive failures. The first is drift. Without a reset, the robot makes a mistake, gets confused, and wanders off into a corner. It drifts so far from its starting baseline that its neural network is suddenly looking at data it has never seen before. It starts outputting garbage commands, flails around, and has absolutely no idea how to recover. The second failure mode is distribution collapse. Say the robot actually succeeds and reaches its goal early. If the simulation doesn't force a reset, the robot just hangs out at the finish line collecting rewards. It gets super good at just existing at the goal, but its state distribution collapses, meaning it completely overwrites and forgets the complex path it took to actually get there.
Let's move to Section 3, pathway forward-backward learning. Okay, so if a human isn't there to constantly reset the environment, the robot has to learn how to become its own reset button. This was one of the major tech pathways developed at Stanford to solve the bottleneck. It works like this. Step 1, the robot executes the forward task, like turning a handle and opening a heavy door. Step 2, it switches gears completely, loading up a dedicated backward policy whose entire job is to undo that task. So, grabbing the open door and pulling it shut. Step 3, it just repeats this cycle autonomously, back and forth, practicing infinitely, while the researchers finally get to go home and get some sleep. But wait, there's a really surprising catch here, highlighted directly in the lecture. The backward task, depending on where the arm starts, can actually be quite a bit harder than the forward task. Just think about the mechanics of that for a second. Pushing a door shut, super simple gross motor movement. Just give it a shove. But grabbing a handle, pulling back, and swinging a heavy door open from a weird angle, that requires immense precision and torque calculation. Or think of a bipedal robot attempting a backflip and falling flat on its face. Figuring out the physics to stand back up from a mangled heap on the floor is a massive computational challenge compared to just jumping. So the crazy irony of this forward-backward pathway is that the robot often spends way more time learning how to clean up its own messes than mastering the actual task. Moving right along to Section 4, Pathway Multitask Cycles. Now, forward-backward learning is absolutely amazing for binary reversible stuff like opening and closing doors. But what happens in highly complex, chaotic environments? Like a messy kitchen. You literally can't unchop a carrot. This is where researchers use something called a task graph. The AI learns that failures aren't dead ends, they're just triggers for the next logical subtask. If the robot tries to put a delicate ceramic cup into a coffee maker but fumbles it onto the floor, it doesn't freeze or sound an alarm for a human. It just checks its internal graph and thinks, the cup is on the floor. My next logical task from this state is to practice my pick up cup from floor skill. The genius here is that every single failure smoothly transforms into an opportunity to practice a different, totally relevant skill. And to make this work at the absolute cutting edge, researchers are now hooking up vision language models, VLMs, which is basically the same tech behind ChatGPT, directly to the robot's cameras. The VLM acts like this brilliant internal coach. It looks at a totally randomized, chaotic kitchen counter, processes the image, and might say, okay, I see an eggplant, a silver pot, and a banana. You can't practice chopping carrots right now because, well, there aren't any carrots in sight. Instead, practice your gripping mechanics by pulling that banana out of the pot. The VLM dynamically proposes new, mathematically useful tasks based on whatever mess the robot just made. It makes the entire learning phase completely self-sustaining. No humans required. And finally, Section 5, Single Life Adaptation, the climax of autonomy. This pathway is pretty much the holy grail of modern robotics. Imagine the robot has finished its thousands of hours of training. It's deployed out into the real world, and boom, it hits a totally weird physical obstacle it has never seen before. It has one single life to figure it out. No safety nets, no resets. Think about how effortlessly you and I solve a physical problem. When you fumble a key in a stubborn lock, you don't just freeze, right? And you definitely don't just blindly jam the key harder until it snaps. You instinctively pull back, reassess the tension, and try a slightly different angle. That split-second, on-the-fly recovery is exactly what we are aiming for with single-life reinforcement learning. The robot has to use its vast library of prior training to adapt instantly to a brand new situation. And this brings us to the massive difference between low-level and high-level adaptation. If a robot only tries to adapt at a low level, which means it just blindly tweaks its micromotor joints to push harder against an unseen obstacle, it's almost always going to overcompensate, flip over, and get stuck permanently like a turtle on its back. But if it's programmed for high-level adaptation, it instantly taps into its library of pre-trained macro skills. It senses a collision and goes, okay, walking straight is failing. Let me instantly trigger my backup skill or my sidestep skill. It acts with strategic, almost human-like common sense to navigate around the problem, instead of just using blind brute force. To wrap up this explainer, I want you to remember this. True, real-world physical autonomy isn't about an AI succeeding perfectly on its very first try. Not at all. It is entirely about mastering the complex math of recovery. Whether it's painstakingly undoing a mistake with forward-backward learning, navigating a web of failures with dynamic task graphs, or adapting on the fly with single-life problem-solving, the real pathway to robotic independence is literally engineering around failure. And that leaves us with a really provocative thought. As we start integrating these autonomous systems into our factories and our daily lives, should we actually be more impressed by a robot that never makes a mistake, or by one that knows exactly how to pick itself back up when it falls? Think about that for a minute.